Hello, in this lecture we'll find out the radius of the small circle. In the drawing we have a circle that is inside a semicircle. We know that line segment CD equals to 3 units and line segment BD equals to 4 units. Angle CDB, this angle is a right angle, it is equal to 90 degrees. And we want to find out the radius of this small circle that is inside the semicircle. This small circle is inscribed by the semicircle. We want to find out the radius of the small circle. Okay, so first of all, we'll do a construction. We'll complete this semicircle to a circle. So we completed the semicircle to a circle, and in the next step we will extend line segment CD by a straight line until it touches the circle. We define the touching point of the extended line segment CD and the circle as point E. So here we know that CD itself is a straight line, and we extended the straight line CD by a straight line. Therefore the result, that is CE, must be also a straight line. So CE is a straight line, and we know that the sum of the angles on one side of a straight line is equal to 180 degrees. So if we focus on this side of the straight line CE at point D, then the sum of the angles on this side of the straight line C at point D must be equal to 180 degrees. So which angles we have at this side of CE at point D? We have here 90 degrees, and angle EDB in total they must be equal to 180 degrees. So I'll write it down. $90 degrees plus the size of angle EDB. In total, they must be equal to 180 degrees according to the rule that the sum of the angles on one side of a straight line is equal to 180 degrees. Okay, so here we will subtract 90 degrees from this equation, and we get that the size of angle EDB is equal to 180 degrees minus 90 degrees, it is 90 degrees. So angle EDB equals to 90 degrees, it is a right angle. So this angle is a right angle. So we know that the new semicircle that we created here, this semicircle is a mirror image of the original semicircle. Okay, and repeat again, the new semicircle that we created by the construction is the mirror image of the original semicircle. And here we also know that angle EDB equals to 90 degrees and angle CDE also equals to 90 degrees. So actually here DE is also the mirror image of CD. Okay? And we know that the mirror image is always the same length of the original image itself, but with opposite direction. That is to say, CD must be equal to DE in its length. I will repeat again. CD must be equal to DE in its length. Why? Because CD by symmetry. Because of the fact that DE is the mirror image of CD, then by symmetry CD must be equal to DE. They have both of those two line segments have the same length but with opposite direction. Exactly as when you look at the mirror, then you see yourself exactly with your exact dimensions, but in the opposite sides. Therefore, CD, DE is the mirror image of CD. Therefore, the lengths of those two line segments, they are equal to each other, but with opposite directions. That is to say, CD equals to DE in its length by symmetry. Okay, but it is given us in the question that CD equals to 3 units. Here CD equals to 3 units, D equals to 4 units. So we know that CD equals to 3 units. So we can write here that CD equals to 3 units. And from this equation, 3 equals to CD equals to DE. We will derive that DE is also equals to 3 units. Okay? Exactly like when you look at yourself in the mirror, you see the exact dimensions of yourself. Your dimensions doesn't change when you see yourself in the mirror, but only the direction of where your image is the opposite. But the length of the dimensions is the same, exactly like here. The length of CD must be equal to DE because DE is the mirror image of CD. Therefore, they have the same length also. That is to say, if CD equals to 3 units, then DE must be also equal to 3 units. Okay? So in the next step, I will present to you a new rule. That is actually rule number 1. According to rule number 1, if two chords intersect with each other inside the circle, if two chords intersect with each other inside the circle, then the following equation is true. So we actually have this circle. In this circle we have two chords that intersect with each other. This is chord AB, intersects with chord CD. This is chord CD. I repeat again. Chord AB intersects with chord CD, the red line, at point O. Point O is the intersection point of chord AB with chord CD. So if this is the data that has been given to us, then according to rule number 1, we will get that AO times OB equals to CO times OD. I'll repeat again. If chord AB intersects with chord CD at point O, that is inside the circle, then according to rule number 1, AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So we actually can implement rule number 1 in our drawing, because in our drawing we have chord AB. This is chord AB. This is chord AB. This is chord AB that intersects with chord CE. This is chord CE at point D. Point D is the intersection point of chord AB with chord CE. Again, point D is the intersection point of chord AB with chord CE. So I write it down in our original drawing. Chord AB, this is chord AB, intersects with chord CE, this is chord CE, at point D. I repeat again, chord AB intersects with chord CE at point D. Point D is the intersection point of chord AB with chord CE. Again, chord AB intersects with chord CE at point D. Point D is the intersection point of chord AB with chord CE. Therefore, so all the requirements of rule number 1 are met. Therefore, we can implement rule number 1 in our drawing. According to rule number 1, we will get that AD times DB equals to CE minus DE. Again, AD times DE equals to CD times DE. So I write it down. AD times DB equals to CD times DE. I repeat again. according to rule number 1, AD times DB equals to CD times DE. Okay? AD is the missing line segment, so we limit as it is. dB equals to 4 units according to what is given us in the question. So we'll substitute dB by 4, and it is equal to CD. CD equals to 4 units according to what is given us in the question. And we just right now found out that D equals to 3 units. So in conclusion, we found out that according to rule number 1, AD times 4 equals to 3 times 3. 3 times 3 is 9. So here, 9 equals to 4 times AD. Here we'll divide this equation by 4, and we get that AD equals to 9 over 4 units. So here AD here found out that line segment AD equals to 9 over 4 units. Okay? And what is, we know that AB is the diameter of the semicircles and also the diameter of the circle itself. Okay? I write it down. AB is the diameter of the circle and the semicircle. Okay, AB is the diameter of the circle and the semicircle, and we know that the diameter is twice as long as the radius. That is to say, AB equals, we define the radius of the big circle as capital R, so AB equals to 2R. Any diameter is twice as long as the radius, so AB equals to 2R. Therefore, R equals to AB over 2. That is to say, what is the length of AB from the drawing? It is to see that AB equals to AD plus DB. AD plus DB equals to AB. All divided by 2. So AB equals to AD plus DB. AD equals to 9 over 4. And it is given us the question that DB equals to 4 units, all divided by 2. Here we multiply 4 by 4 and then we divide it by 4 in order to have a common factor with 9 over 4. So here we will have 9 plus 4 times 4 is 16 over 4 over 2. 9 plus 16 is 25. Divided by 4 over 2. Here we'll move 2 to the denominator and we get that the radius of the big circle, that is also the radius of the semicircle, that is equal to capital R according to our definition, equals to 25 over 4 times 2. 4 times 2 is 8, so it is 25 over 8 units. So, in conclusion, the radius of the circle, the big circle, that is also the radius of the semicircle, that is equal to capital R, it is equal to 25 over 8 units. Okay? In the next step, we will define the radius, the center of the big circle, SP. The center of the big circle is also the center of the semicircles, of course. So point P is the center of the circle and the semicircle. And we'll define SQ, the center of the small circle. Okay? So here, what is the length of DP? Here, from the drawing, you can see that the length of the short line segment DP is equal to DB minus PB. DB minus PB. I repeat again, it is very easy to see from the drawing that the length of the short line segment DP equals to DB minus PB. Okay, I repeat again, DP equals to DB minus PB. DB equals to 4 units, it is given as the question. And what is the definition of line segment PB? Line segment PB starts from the center of the big circle and ends at point B, that is a point on the big circle itself. That is to say, this is exactly the definition of a radius. That is to say, PB is the radius of the big circle, that is capital R. So in conclusion, we found out that DP equals to 4 minus capital R, but we have already found out that capital R equals to 25 over 8. Here, capital R equals to 25 over 8. So we substitute capital R by 25 over 8, and we get that the length of the short line segment DP equals to 4 minus capital R, that is 25 over 8. Here we will multiply 4 by 8 and then we'll divide it by 8 in order to have a common factor with 25 over 8. And we will get that the length of the short line segment DP equals to 4 times 8 is 32 minus 25 over 8. 32 minus 25 is 7. In conclusion, DP equals to 7/8. DP equals to 7/8. So we can write here that DP equals to 7/8. Okay. Here, from point Q, we will draw, that is the center of the small circle, we will draw the radius that is drawn to the point of tendency. First of all, we will define the point of tendency here. We will define the point of tendency of tangent DB with this small circle as point M. Again, point M is the point of tendency of tangent DB with this small circle. And from point Q, we'll draw, first of all, we'll define the radius of the small circle as small r. And then from point Q, we'll draw the radius QM that is drawn to the point of tendency. Here, QM is defined as the radius of the small circle, that is to say it is equal to small r. So here we have the radius QM, it is drawn to the point of tendency. That is to say, the radius QM, it is drawn to point M, that is the point of tendency of tangent DB with this small circle. And whenever you have a radius that is drawn to the point of tendency, then the tangent will be perpendicular to that radius. Again, DB is perpendicular to QM. So if DB is perpendicular to QM, that is to say this angle equals to 90 degrees, and this angle will be also equal to 90 degrees according to the rule that I have already mentioned. A tangent to a circle is perpendicular to the radius that is drawn to the point of tendency. So whenever you have a radius that is drawn to the point of tendency, like in this drawing, the radius QM, it is drawn to point M, that is the point of tendency of tangent DB with this small circle, then the tangent DB will be perpendicular to that radius. In this case, DB will be perpendicular to MO, that is to say this angle equals to 90 degrees, and this angle equals to 90 degrees also. Likewise, from the center of the small circle, we will draw the radius that is drawn to the point of tendency. The point of tendency of tangent CD with this small circle, we define it as L. So here QL is the radius of the small circle, that is to say it is equal to small r. Why QL is the radius of the small circle? Because of the fact that line segment QL starts from point Q, that is the center of the small circle, and ends at point L, that is a point on the small circle itself. And this is exactly the definition of a radius. That is to say, QL is the radius of the small circle that is equal to r, small r. And here we have the radius QL, it is drawn to the point of tendency. That is to say, it is drawn to point L, that is the point of tendency of tangent CD with this small circle. And whenever you have a radius that is drawn to the point of tendency, then the tangent will be perpendicular to this radius. Here, CD perpendicular to RQ. Again, CD is perpendicular to RQ, that is to say, this angle equals to 90 degrees, and this angle will be also equal to 90 degrees. Okay? I've already mentioned the rule that is related to the radius that is drawn to the point of tendency, so I'll not repeat on it. So here, in quadrilateral LQDM, this quadrilateral LQDM, we have 1, 2, 3 right angles. Again, in quadrilateral LQDM, we have 1, 2, 3 right angles. I'll write it down. in quadrilateral LQDM, we have three right angles. The sum of three right angles is 90 times 3 is 270 degrees, plus the size of the fourth angle, that is actually angle LQM, this angle. In total, the sum of those four angles must be equal to 360 degrees. Here. 270 degrees. That is the sum of the three right angles inside quadrilateral LQDM plus the size of the fourth angle, that is actually angle LQM. In total, they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Here we'll subtract 270 degrees from this equation, and we get that the missing angle, angle LQM, is equal to 360 degrees minus 270 degrees, it is equal to 90 degrees. That is to say, angle LQM, it is a right angle. So we can write here that angle LQM, this angle is a right angle, it is equal to 90 degrees. So actually, quadrilateral LQDM has four right angles, and therefore quadrilateral LQDM is a rectangle. So write it down. Quadrilateral LQDM is a rectangle because it has four right angles. Actually, quadrilateral LQDM is at least a rectangle. In this specific case, if we analyze quadrilateral LQDM, we will reveal that it is not a rectangle but a square, but we will relate to quadrilateral LQDM as a rectangle. It is at least a rectangle, if not a square. So we relate to quadrilateral LQDM as a rectangle, and we know that the opposite sides of a rectangle are equal to each other, that is to say LQ equals to DM. In quadrilateral LQDM, LQ equals to DM. According to the rule that the opposite sides of a rectangle are equal to each other. But we have already found out that LQ is the radius of the small circle, that is to say it is equal to small r. So we can write here that LQ equals to small r. And from this equation, r equals to LQ equals to dm, we will derive that dm is also equals to r. dm equals to r. So we can write here that dm equals to r. Small r, that is the radius of the small circle. So what is the length of PM? What is the length of PM? The length of line segment PM, from the drawing it is very easy to see that the length of line segment PM equals to dm minus dp. dm minus dp equals to PM. I'll repeat again. PM equals to dm minus dp. Okay, PM equals to dm minus dp. So PM equals to dm. We just right now found out that dm is the radius of the small circle, that is to say it is equal to small r minus dp. We already found out that dp equals to 7/8, so we substitute dp by 7/8. So in conclusion, we found out that the length of line segment PM equals to r, small r minus 7/8. Okay, so we can write here that PM equals to small r minus 7/8. Okay. In the next step, I will present to you a new rule that is actually rule number 2. According to rule number 2, in an internal lunge between two circles, the straight line that connects the two centers together passes through the lunge point. And the lunge point is the point of tendency of the two circles. Point of tendency of the two circles. The point of tendency of the two circles, or the touching point of the two circles, it is the same. So I will read rule number 2 again. According to rule number 2, in an internal lunge between two circles, the straight line that connects the two centers together passes through the lunge point of the two circles. So here we are talking about internal lunge. Two circles can touch each other in two different ways. If they touch each other externally, then this is another case, but in our specific case, we are talking about those two circles that touch each other internally. That is to say, the small circle is inside the big circle, and this is the point of tendency, or the launch point between those two circles. We define the launch point, or the point of tendency of those two circles as point S. So here, this is point S is the touching point between those two circles, the small circle and the big circle, or the point of tendency, or the launch point of those two circles. This is actually the case of the internal launch. The small circle touches the big circle internally, that is to say, the small circle is located inside the big circle and touches the big circle internally. So in this case, when the two circles touch each other internally, like in this drawing, then the center, the straight line that connects the two centers together, that is to say, it is PQ. Why? Because P is the center of the big circle and Q is the center of the small circle. Okay? So here, this straight line again, PQ, this straight line PQ is a straight line that connects together the two centers, P and Q. And according to rule number 2, this straight line PQ passes through the launch point, that is to say, point S is the launch point between those two circles. That is to say, according to rule number 2, the straight line PQ that connects the two centers together, P and Q, passes through point S. That is to say, here PQS is one straight line. Okay, here PQS is one straight line. That is to say, points P, Q, and S, they are all lying on the same straight line. Again, points P, Q, and S, they are all lying on the same straight line. Okay, this is the meaning of rule number 2. So here, what is the definition of QS? Q is the center of the small circle. S is a point on the small circle itself. This is exactly the definition of a radius. That is to say, QS is the radius of the small circle that is equal to small r. And what is the definition of line segment PS? P is the center of the big circle. S is a point of the big circle itself. This is exactly the definition of a radius. That is to say, PS is equal to the radius of the big circle, that is actually equal to capital R, that is 25 over 8 units. Okay, I repeat again, line segment PS is the radius of the big circle, that is also the radius of the semicircle, that is to say, it is equal to capital R, that is 25 over 8 units. Okay, and what is the length of line segment PQ? The length of line segment PQ it is equal to, from the drawing, it is very easy to see that the length of line segment PQ, it is very easy to see that PQ equals to PS minus QS. PS minus QS. Again, PQ, this line segment PQ equals to PS minus QS. Again, PS minus QS equals to PQ. Okay, here we found out that PQ equals to PS minus QS. And we have already found out that PS is the radius of the big circle, that is capital R. PS, line segment PS is defined as the radius of the big circle that is equal to capital R. We will substitute PS by capital R because it is the radius of the big circle that is equal to capital R minus QS. And we have already found out that QS equals to small r. So in conclusion, PQ equals to capital R minus small r. That is to say, PQ equals to capital R, that is 25 over 8, minus small r. Small r is the missing line segment in this question. This is the variable that we are looking for in this question. So we can write down here that PQ equals to 25 over 8 minus r. Okay, so in the next step we can actually implement the Pythagoras theorem in the right triangle PQM. The only missing variable in this right triangle PQM is r, and by implementing the Pythagoras theorem on the right great triangle PQM, we will find out the value of r, that is the radius that we are looking for in this question, in this lecture. So I copy the right triangle PQM in a new page, and we will implement the Pythagoras theorem on this green right triangle PQM. Okay? So we have the right triangle PQM. This is the right triangle PQM that I copied from the original drawing. We have already found out that PQ equals to 25 over 8 minus r. 25 over 8 minus small r. We have already found out that PM equals to small r minus 7/8. And there we have already found out that QM is the radius of the small circle, that is to say it is equal to small r. Why? Because point Q is the center of the small circle. Point M is a point on the small circle itself, and this is exactly the definition of a radius. So QM equals to small r. So in the right triangle QPM, by PT is abbreviation for Pythagoras theorem. By PT, according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, the hypotenuse in this right triangle is PQ. Therefore, the square of the hypotenuse is PQ squared, and it is equal to the sum of the squares of the perpendiculars. That is to say, it is equal to OQM squared plus PM squared. I repeat again, we implemented the Pythagoras theorem on the right triangle PQM. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, PQ square equals to QM square plus PM square. We have already found out that, according to the Pythagoras theorem, of course. So here we have already found out that PQ equals to 25 over 8 minus r. Therefore, PQ square is 25 over 8 minus r squared. That is equal to QM. QM equals to r, so QM square is r squared plus PM. PM equals to R minus 7/8. So therefore PM squared will be equal to R minus 7/8 squared. Here we will open the brackets on both sides of this equation, equation number 1. And we'll get that according to equation number 1, 25 minus R squared, according to the equation that A minus B equals to A minus B squared equals to A squared plus B squared minus 2 times AB. Therefore, 25 over 8 minus R squared is 25 over 8 squared, that is 25 squared is 625, and 8 squared is 64. Okay, plus B squared is plus R squared minus 2 times 25 over 8 times R. And it is equal to R squared plus R minus 7/8 squared is equals to R squared plus 7/8 squared, that is actually 7 squared is 49 and 8 squared is 64, minus 2 times R times 7/8. Okay? So here we have, in this side of equation number 1, we have 625 over 64 plus R squared minus, so we have here minus 2 times 25 R over 8. We divide both the numerator and the denominator of this expression by 2. Minus 2 over 2 is minus 1, so here 2 will get cancelled. So in the denominator we left only with minus 25R. In the numerator we are left only with minus 25R. And the denominator we have 8. 8 over 2 is 4. So in conclusion, this expression equals to minus 25R over 4. In the other side of the equation number 1, we have R squared plus R squared plus 49 over 64. Here we have minus 2R times 7 over 8. We'll divide both the numerator and the denominator of this expression by 2. Minus 2 over 2 is minus 1, so in the numerator we left only with minus 7R. In the denominator we have 8. 8 over 2 is 4. So in conclusion, this expression, minus 2R times 7 over 8 equals to minus 7R over 4. Okay, so we actually got this equation number 1. Here we have R squared on both sides of equation number 1, so R squared will get cancelled. And what is left from equation number 1 after we cancelled R squared? We have here actually we will multiply equation number 1 by 64. So here 625 over 64 times 64 is 625. Here we have minus 64 over 4 is minus 16. So in conclusion, this expression will be equal to minus 16 times 25r. In the other side of equation number 1, we have r squared times 64 is 64r squared. And here we have 64 over 64 is 1, so what is left from this expression is only 49. Minus 64 over 4 is minus 16, so this expression equals to minus 16 times 7r. Okay? So here we have, in this side of equation number 1, we have 625. Minus 16 times minus 25r is minus 400r. That is equal to 64r squared plus 49 minus 16 times 7r is minus 112r. So here we will add 400r to this equation, equation number 1, and we will get that according to equation number 1, $625 equals to 400r minus 112r is plus 288r. Plus 64r squared plus 49. Here we subtract 625 from this equation, equation number 1, and we get here 625 minus 625 is 0. Equals to, we have here 64r squared plus 288r, and here 49 minus 625 is minus 576. So in conclusion, we found out that according to equation number 1, 64r squared plus 288r minus 576 equals to 0. So we have here a quadratic equation. We will divide this quadratic equation by 32, and we'll get that 0 over 42 is 0. 64 over 42 is 2, so here we will have 2r squared plus 288 over 32 is 9, so plus 9r, minus 576 over 42 is minus 18. So in conclusion, we got the quadratic equation that 2r squared plus 9r minus 18 equals to 0. So in this quadratic equation, the coefficient A equals to 2, the coefficient B equals to 9, and the coefficient C equals to minus 18. And the variable that we are looking for in this quadratic equation is r, so x equals to r. And the general formula to solve a quadratic equation is x equals to minus b plus minus square root of b squared minus 4 times ac over 2a. In our specific quadratic equation, x equals to r, so we substitute x by r, and we get that r equals to minus b. B equals to 9, so minus b is minus 9, plus minus square root of b squared. B is 9, so b squared is 9 squared, that is 81, minus 4 times a is 2, times c is minus 18, over 2a. A is 2, so 2a is 2 times 2, that is 4. So here we have the radius of the small circle. It will be equal to minus 9 plus minus. Here we have inside the root 81, and here minus 18 times 2 is minus 36. Minus 36 times minus 4 is plus 144. So inside the root we left only with 144 plus 81, all divided by 4. So here r equals to minus 9 plus minus 81 plus 144 is 225. So inside the root we left only with 225 over 4. So here we will have two solutions that are possible for r. The first solution for r, that is the radius of the small circle. It is equal to minus 9, and it is minus 9 plus minus the square root of 225 is 15 over 2. So here we will have two solutions that are possible for r. The first solution for r is that r equals to minus 9 minus 15, all divided by 4, of course, not 2, by 4, all divided by 4. Minus 9 minus 15 is minus 24 over 4. Minus 24 over 4 is minus 6. So we found out that the radius of the small circle equals to minus 6. This is a negative number, but r is the length of the radius of the small circle. I repeat again, r is the length of the radius of the small circle. And because of the fact that r is a length, as a length it must be a positive number. So it can never be equal to minus 6, that is a negative number, so we'll cancel the solution, and we're left only with the second solution for r, that r equals to minus 9 plus 15 over 4. Minus 9 plus 15 is 6 over 4. So here r equals to 6 over 4. We divide both the numerator and the denominator of this side of the equation by 2, and we get that 6 over 2 is 3, and 4 over 2 is 2. So in conclusion, we found out that r equals to 3 over 2 units, or we can represent it also as 1.5 units. And that is the answer to the question, r, the radius of the small circle, it is equal to either 3 over 2 units, or in terms of numbers, it is equal to 1.5 units. Here, r, the radius of this small circle is equal to either 3 over 2 units, so in terms of numbers it is equal to 1.5 units. In the next step I will summarize the lecture. Okay. So actually we have here a circle that is inscribed by a semicircle. We know that CD equals to 3 units, DB equals to 4 units, angle CDB equals to 90 degrees, and we want to find out the radius of the small circle. Okay? So first of all, we did a construction. We completed the semicircle to a circle. I repeat again, in order to find out the radius of this small circle, we did the construction, we completed this semicircle to a circle, and actually here we created the second semicircle here. This second semicircle is a mirror image of the original semicircle. Actually, every circle has 2 semicircles, and one semicircle is the mirror image of the other semicircle. Okay, in this case, we created the second semicircle, and this second semicircle is a mirror image of the original semicircle. Okay? Then we extended the straight line CD by a straight line until it touches the circle at point E. Point E is the touching point of the extended CD and this circle. Okay? And we know that CD is a straight line, and when we extended the straight line CD by a straight line, the result must be a straight line, because when you extend a straight line by a straight line, the result must be a straight line. Therefore, CE must be a straight line. And we have the rule that the sum of the angles on one side of a straight line is equal to 180 degrees. So if we focus on this side of the straight line CE at point D, then the sum of the angles on this side of CE at point D must be equal to 180 degrees. So which angles we have at point D? We have here 90 degrees, and this angle EDB. So here here 90 degrees plus the size of angle EDB must be equal to 180 degrees, according to the rule that the sum of the angles on one side of a straight line equals to 180 degrees. We subtracted 90 degrees from this equation and found out that angle EDB, the missing angle, here this angle EDB is the right angle. This is to say it is equal to 90 degrees. Okay, so here we have angle CDB is a right angle, and angle EDB is also a right angle. Okay, so actually, because of the fact that the new semicircle that we created by the construction is the mirror image of the original semicircle, it means that when we draw the straight line DE, we actually draw both the mirror image of CD. Okay? We know that angle CDE equals to 90 degrees, and angle EDB is also equal to 90 degrees. Okay? Therefore, ED is the mirror image of CD. Because of the fact that ED is the mirror image of CD, it means that their lengths must be equal to each other, because when you look at yourself in a mirror, then your dimensions doesn't change. The only thing that is changed when you look at yourself in a mirror is the direction of yourself. You see yourself in the opposite direction, but your dimensions doesn't change at all. So when we draw the mirror image of CD, that is DE. So DE is the mirror image of CD, and the only thing that is changed in the mirror image is the direction. The direction of CD and DE is the opposite direction, and the common point is point D. They have opposite directions, but their lengths must be the same length. Okay? So here, because of the fact that DE is the mirror image of CD, it means that the lengths of those two line segments must be equal to each other, because the mirror image is always the same length of the image itself, and the only thing that is changed in the mirror image is the direction. Okay? But the lengths of those two line segments must be equal to each other, because the length of the original image must be equal to the length of the mirror image. So CD equals to DE because of the fact that DE is the mirror image of CD, therefore they have the same lengths. That is to say, CD equals to DE. Okay, CD equals to DE by symmetry. But we know that CD equals to 3 units. It is given us the question, CD equals to 3 units, so from this equation 3 equals to CD equals to DE, we derive that DE is also equals to 3 units. Okay, here DE equals to 3 units also. Then I presented to you a new rule, that is actually rule number 1. According to rule number 1, if two chords intersect with each other inside the circle, then the following equation is true, that AO times BO, AO times BO equals to CO times DO. I repeat again, inside this circle we have two chords, chord AB and chord CD. Chord AB intersects with chord CD at point O. Point O is the intersection point of those two chords. Therefore, the following equation is true, according to rule number 1, that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. Okay? So we actually can implement rule number 1 in our drawing. Why? Because in our drawing, we have chord AB intersects with chord CE at point D. I repeat again. Chord AB intersects with chord CE at point D. Point D is the intersection point of chord AB with chord CE. So all the requirements of rule number 1 are satisfied. They are met. Therefore, we can implement rule number 1 in our drawing. According to rule number 1, we get that AD times DB equals to ED times DC. Again, AD times DB equals to ED times DC. I repeat again, AD times DB equals to CD times DE according to rule number 1. AD times DB equals to ED times DC according to rule number 1. AD is the missing line segment. According to what is given us the question, DB equals to 4 units. Here, CD equals to 3 units. CD equals to 3 units according to what is given us the question, so we substitute CD by 3. And we just right now found out that DE equals also to 3 units, so we substitute DE by 3. In conclusion, we found out that AD times 4 equals to 3 times 3. 3 times 3 is 9. So here we found out that 4 times AD equals to 9. We divided this equation by 4 and found out that AD equals to 9 over 4. So here AD equals to 9 over 4 units. Okay? Then we know AB, before the construction, we have the semicircle with AB, that is actually the diameter of the semicircle, that is also the diameter of the circle itself, of course. So we know that AB is the diameter of the circle itself, and it is also the diameter of the semicircle. Why? Because the semicircle and the circle itself have the same diameter. So AB is the diameter of the semicircle and the circle, and we know that the diameter of any circle, of any semicircle, it is twice as long as the radius. That is to say, AB equals to 2r if r is the diameter of the circle and also the diameter, if r is the radius of the circle itself and also the radius of the semicircle, then 2 times the radius of the circle of the semicircle equals to the diameter, that is AB. So if we divide this equation by 2, we get that the radius of the semicircle and the circle itself, it is half of the diameter. It is AB over 2. AB equals to AD plus DB. And all divided by 2. AD, we just right now found out that AD equals to 9 over 4. DB equals to 4 units. It is given us the question. So in conclusion, AB, R equals to 9 over 4 plus 4 over 2. Here we multiplied 4 by 4 and we divided by 4 in order to overcome a factor with 9 over 4. So here 4 times 4 is 16. So here we have 16 plus 9 over 4 over 2. 16 plus 9 is 25. 25 over 4 over 2. So we moved 2 to the denominator and found out that R, the radius of the circle itself, it is also the radius of the semicircle, it is equal to 25 over 4 times 2. 4 times 2 is 8, so in conclusion found out that the radius of the circle itself, that is also the radius of the semicircle, equals to 25 over 8 units. Okay, then we found out the length of the short line segment DP. From the drawing, we can see that dP equals to dB minus PB. Again, dP equals to dB minus PB. dP equals to dB minus PB. dB equals to 4 units according to what is given as the question. PB, what is PB? First of all, we actually defined point P as the center of the big circle and point Q is the center of the small circle. So P is the center of the big circle. B is a point of the big circle itself, and this is exactly the definition of a radius. That is to say, PB equals to capital R, that is the radius of the big circle. Okay, PB equals to capital R, or B equals to 4, so in conclusion we found out that DB equals to 4 minus capital R. And we already found out that capital R equals to 25 over 8, so we can substitute R by 25 over 8. We did it and we got that dP, the small line segment dP, equals to 4 minus 25 over 8. Here we multiplied 4 by 8 and then we divided by 8 in order to overcome a factor of 25 over 8. And we got here that dP equals to 8 times 4 is 32 minus 25 over 8. 32 over 25 is 7, so in conclusion we found out that dP, the small line segment, this small line segment dP equals to 7/8. Okay? So here from point Q we drew the radius to the point of tendency, that is actually point L. Point L is the point of tendency D with this small circle. Again, point L is the point of tendency of tangent CD with this small circle. So we have the radius L, the radius QL, it is drawn to the point of tendency. That is to say, it is drawn to point L, that is the point of tendency of tangent CD with this small circle. And whenever you have a radius that is drawn to the point of tendency, then the tangent will be perpendicular to that radius. In this case, tangent CD will be perpendicular to the radius LQ. So if CD is perpendicular to LQ, it means that this angle equals to 90 degrees and this angle will be also equal to 90 degrees, according to the rule that I mentioned in the previous lectures, that a tangent to a circle is perpendicular to the radius drawn to its point of tendency. Likewise, from point Q, we draw radius to the point of tendency, that is point M. Point M is the point of tendency of tangent DB with this small circle. And whenever you have a radius, that is to say QM is the radius that is drawn to the point of tendency, that is to say the radius QM, it is drawn to point M, that is the point of tendency of tangent DB with this small circle, then in this case, if the radius is drawn to the point of tendency, then the tangent DB will be perpendicular to the radius MQ. DB is perpendicular to MQ, that is to say this angle equals to 90 degrees and this angle will be also equal to 90 degrees. So actually, in quadrilateral LQDM, this quadrilateral, we have 1, 2, 3 right angles. And the sum of 3 right angles is 90 times 3 is 270 degrees, plus the size of the fourth angle, that is actually angle LQM. In total, they must be equal to 360 degrees. Here, angle in quadrilateral LQM, the sum of 3 right angles is 90 times 3 is 270 degrees, plus the size of the fourth angle, that is actually angle LQM. In total, they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. We subtracted 90 degrees from this equation, and we found out, we subtracted 270 degrees from this equation, and we found out that the missing angle LQM equals to 360 degrees minus 270 degrees, it is 90 degrees. So here the missing angle LQM equals to 90 degrees. Therefore, we actually found out that all 4 angles inside quadrilateral LQDM are right angles, and any quadrilateral that has 4 right angles must be at least a rectangle. So we relate to quadrilateral LQDM as a rectangle. Okay? So, but we know that the opposite sides of a rectangle are equal to each other. So in rectangle LQDM, its opposite sides are equal to each other. That is to say LQ equals to DM. LQ equals to DM according to the rule that the opposite sides of a rectangle are equal to each other. Okay? But we have already found out that LQ equals to R. It is the radius of the small circle. So we can write here that LQ equals to R, the radius of the small circle. And from this equation, R equals to LQ equals to DM, we derive that DM is also equals to R. Here, DM is also equals to R. DM equals to R, that is the radius of the small circle. And what is the length of line segment PM? The length of line segment PM equals to DM minus DP. Again, PM equals to DM minus DP. Yeah. PM equals to DM minus dP. So PM equals to DM. We just right now found out that DM is the radius of the small circle, that is to say it is equal to small r. So DM equals to small r. And dP, we have already found out that dP equals to 7/8. So in conclusion, we found out that PM equals to r minus 7/8. Here, PM equals to r minus 7/8. Then I presented to you rule number 2. According to rule number 2, in an internal lunge between 2 circles, the straight line that connects the two centers together passes through the launch point of the two circles. Okay, I repeat again. In an internal launch between, or if there is an internal launch between two circles, then the straight line that connects the two centers together passes through the launch point of the two circles. In our case, we have an internal launch between those two circles. Why? Because of the fact that the small circle is inside the big circle and touches the big circle at this point, point S. Point S is the launch point, or the point of tendency, or the touching point of the small circle with the big circle. Therefore, we have, in this case, internal launch between the small circle and the big circle. So this is the case of the internal launch, and according to rule number 2, whenever you have an internal launch between two circles, then the straight line that connects the two centers together, that is to say PQ, P is the center of the big circle, Q is the center of the small circle, and the straight line that connects the two centers together is PQ. That straight line PQ must pass through the launch point that is PS. That is to say PQS. Those 3 points PQS are located on the same straight line. PQS are located on the same straight line because the straight line PQ must pass through the launch point that is point S. That is to say PQS is one straight line. Okay, whenever you have an internal launch between two circles like in this drawing, then the straight line that connects the two centers together PQ must pass through the launch point that is point S. So PQS are located on the same straight line, or PQS is one straight line. Okay? So if PQS is one straight line, then what is the length of QS? Q is the center of the small circle. S is a point of the small circle itself, and this is exactly the definition of a radius. That is to say QS is the radius of the small circle, that is to say it is equal to small r. Okay, and what is the length of PS, or what is the definition of line segment PS? P is the center of the big circle. S is a point on the big circle itself, and this is exactly the definition of a radius. That is to say PS is the radius of the big circle, that is to say it is equal to capital R. Okay, and what is the length of line segment PQ? Here, PQ, you can see that PQ equals to PS minus QS. Again, PS minus QS equals to PQ. I'll repeat again, PQ equals to PS minus QS. Okay, that is to say PQ equals to PS. We have already found out that PS is the radius of the big circle, that is to say it is equal to capital R, and QS is the radius of the small circle, that is to say it is equal to small r. So in conclusion, we found out that PQ, the length of line segment PQ, is capital R minus small r. Capital R, the radius of the big circle, equals to 25 over 8. So we substitute capital R by 25 over 8. So in conclusion, we found out that PQ, that is the hypotenuse of this right triangle, it is equal to 25 over 8 minus r. Here PQ equals to 25 over 8 minus r. We have already found out that PM equals to small r minus 7/8, and QM equals to R. This is the radius of the small circle. So I copied the right triangle in this new page, and we implemented the Pythagoras theorem on this triangle QPM. The only missing variable in this right triangle is R, so by implementing the Pythagoras theorem on this right triangle, we will find out the radius R, that is the radius of the small circle, the radius that we are looking for. Okay, so here According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is PQ, therefore the square of the hypotenuse is PQ squared, and it is equal to the sum of the squares of the perpendiculars. That is to say, it is equal to QM squared plus PM squared. Okay, so according to Pythagoras theorem, PQ squared equals to QM squared plus PM squared. PQ equals to 25 over 8 minus R, so we substitute PQ by 25 over 8 minus R. Then we squared it, because PQ squared, it is 25 over 8 minus R squared, equals to QM squared. QM equals to R, small r, so QM squared is small r squared. PM equals to R minus 7/8, so PM squared is R minus 7/8 squared. Then we open the brackets on both sides of this equation, equation number 1, and found out that 25 over 8 minus r squared, according to the algebraic identity, that a plus a minus b squared equals to a squared plus b squared minus 2 times ab. We get that 25 over 8 minus r squared equals to 25 over 8 squared, that is 625 over 64, plus r squared minus 2 times 25 over 8 times r. And it is equal to, on the other side of the equation, we have r minus 8 squared, that is r squared minus plus 7/8 squared, that is 49 over 64, minus 2 times r times 7/8 times 7/8. Okay, then here we have we divided both the numerator and the denominator of this expression by 2. So here minus 2 over 2 is minus 1, so 2 will get cancelled. And the denominator we have 8, so 8 over 2 is 4. So in conclusion, this expression equals to 25 r over 4. Okay, this expression equals to 25 r over 4. So here we have 625 over 64 plus r squared minus 25 r over 4, that is equal to r squared plus r squared plus 49 over 64, and here we have minus 2r times 7 over 8. We divided both the numerator and the denominator of this expression by 2. Minus 2 over 2 is minus 1, so 2 will get cancelled. So in the numerator we left only if minus 7r, and in the denominator we have 8. 8 over 2 is 4. So in conclusion, this expression equals to minus 7r over 4. Then we multiply this expression by 64. But first of all, we have r squared on both sides of this equation, equation number 1, so r squared will get cancelled. Then we multiply this equation, equation number 1, by 64. 625 times 64 over 64 is 625. And here we have 64 minus 64 over 4 is minus 16. So in conclusion, this expression equals to minus 16 times 25r. And here we have 64 times r squared is 64r squared, and 49 times 64 over 64 is 49, and here we have minus 64 over 4 is minus 16. So in conclusion, this expression equals to minus 16 times 7r. Okay, and here minus 16 times 25r equals to minus 104. Again, minus 16 times 25r equals to minus 400r. and here minus 16 times 7r equals to minus 112r. So in conclusion, I found out that according to equation number 1, 625 minus 400r equals to 64r squared plus 49 minus 112r. Here we added 400r to this equation, equation number 1. So here 400r minus 400r is 0. So we left here only with 625, and the other side of the equation we have 64r squared plus 49, and here we have 400r minus 112r. 400r minus 112r is 288r. Okay, so here this 288r plus 64r squared plus 49, that is equal to 625, because here 400r minus 400r is 0, so we left only here with 625, that is equal to 288r plus 64r squared plus 49. We subtracted 625 from this equation, and we found out that according to equation number 1, 625 minus 625 is 0. So we have here 0 plus 600r squared plus 288r, and here we have 49 minus 625, again 49 minus 625 equals to minus 576. So in conclusion, according to equation number 1, we found out that 0 equals to 664r squared plus 288r minus 576. We divided this equation number 1 by 32, and found out that 64 over 32 is 2, so this expression equals to, in total, to 2r squared. 288r over 32 is 9r, and minus 576 over 32 equals to minus 18. So in conclusion, we found that we have here the quadratic equation that 2r squared plus 9r minus 18 equals to 0. In this quadratic equation, the coefficient a equals to 2, the coefficient b equals to 9, and the coefficient c equals to minus 18. And the variable that we are looking for in this quadratic equation is r, so x equals to r. And the general formula for solving a quadratic equation is x equals to minus b plus minus square root of b squared minus 4 times ac over 2a. And here x equals to r, so we substitute x by r, and we get that r equals to minus b equals to 9, so minus b is minus 9 plus minus square root of b squared. B equals to 9, so b squared is 9 squared, that is 81, minus 4 times a is 2, times c is minus 18 over 2a. A is 2, so 2 times 2 is 4. So here we get that r equals to minus 9 plus minus. Inside the root we have 81, and here we have minus 4 times 2 is minus 8, and minus 8 times minus 18 is plus 144. So inside the root we have in conclusion 81 plus 144 all divided by 4. 81 plus 144 is 225. So in conclusion, we found out that r equals to minus 9 plus minus square root of 225 over 4. Okay. And the square root of 225 is 15. So in conclusion, we found out that the radius r, the radius of the small circle, equals to minus 9 plus minus 15 over 4. So here we will have two solutions that are possible for r. That is the radius of the small circle. The first solution for r is r equals to minus 9 minus 15 over 4. Minus 9 minus 15 is minus 24, and minus 24 over 4 is minus 6. So we found out that r equals to minus 6, that is a negative number, but r is the length of the radius of the small circle, and r as a length, it must be a positive number. R as a length, it must be a positive number. It can never be equal to minus 6, that is a negative number. So we cancel the solution, and we're left only with the second solution, that r equals to minus 9 plus 15 over 4. Minus 9 plus 15 is 6, so r equals to 6 over 4. We divided both the numerator and the denominator by 2. 6 over 2 is 3, and 4 over 2 is 2. So in conclusion, found out that r, that is the radius of the small circle, it is equals to either 3 over 2 units, or in terms of numbers, r equals to 1.5 units. I will repeat again, r, that is the radius of this small circle, it is equal to either 3 over 2 units, or in terms of numbers, it is equal to 1.5 units. Okay, thank you very much.